The first part of this class, part 1, is Finite Difference Method. FDM for steady state problems. We'll start with a partial differential equation, PDE. Ut is equal to a of x, ux, x plus f of x. It has two variables. U is a function of x and t, location and time. That's why this is called a PDE. And without getting too much into PDE theory, what this models, for example, it models many things, but one thing it models is a temperature distribution of a rod from A to B, for example, and F would be some kind of source term. There's a fire somewhere. F is source term, and we are given a initial condition, which is when t is equal to 0. The initial temperature distribution of this rod. And there are many kinds of boundary conditions we can give. One kind is so-called Dirichlet boundary condition, which is the left end, the two end, the temperature for the two ends are fixed. Maybe it's immersed in ice water, for example. So I'm going to use UL, UR. U on the left is equal to UL fixed, on the right is fixed at UR. And this is so-called Dirichlet boundary condition, BC for boundary condition. This is so-called transient. So the temperature is changing as time goes by from, at least initially, it's a transient state. It changes, okay? Versus so-called steady, which is, i.e., when your time is infinity, you let this system evolve to infinity. And for some system, including this one included, it reaches so-called steady state. Steady state. So what do we mean by steady state? A steady state, it means things are not changing with time, right? So it means U sub t is equal to 0. Its partial derivative with respect to time is 0. That means it's steady. It's not changing with time. Which means that once we put ut equal to 0 in the original PDE, we're going to get a equation negative ax, ux, a is, by the way, the conductivity of the material, x is equal to f of x, okay? And we have that the boundary condition is still there, or UL. Now U is only a function of x because it's not changing with time. UA is equal to UL. UB is equal to UR, right? So that's basically the equations that we're going to focus on for the first part is coming from. I do want to at least mention the so-called higher dimension case. In high dimension, if instead of a rod, it's a it's a plate, for example, it's a plate, 2D. Then this equation corresponds to divergence. Is divergence of AX gradient of U is equal to F. Okay. So for example, 2D, right? U would be a function of X and Y. So as you may recall, gradient of U is U sub X, U sub Y, the row vector, take a transpose, is a column vector, and AX is a 2x2 matrix. All right, 2x2 matrix. And what's the divergence? Divergence of a vector here, right? Of a vector VW is Vx plus Wy. Okay. So in particular, if A is an identity matrix, right? It's 1, 1 on the main diagonal and 0 as well, then we're going to get divergence of the gradient of U, which is Ux, Uy. So that is Ux, take another X, XX, plus U, YY. That's exactly the Laplacian of U, right? Laplacian of U. Laplacian of U. So Laplacian of U is a 2D version. This is 2D version of U double prime, all right, in the 1D, or when it only has one variable X, U XX. So in this class, we're concerned about solving the equations numerically, as we alluded to in the last semester. So why we want to do that is that the most differential equation, DE for differential equation, we will need computers to solve. Need computers to, and of course software on the computers to solve for a approximate solution. And there are many different methods and related methods. One is what we're doing here, finite difference, FDM. And others are FVM, V for volume. And that one's called FEM, finite element. We'll talk a little bit about finite element, like the most basic things. And there's another method called spectral. Just to give you some names, so we're not going to do any of those in any detail, other than FDM and a little bit of finite element. So the overarching theme of finite difference is that it uses divided difference. Differences to replace derivatives. To replace derivatives of differential equations, right? First derivative, second derivative, and so on and so forth. So of course, the question then is how to do it, right? How to do it. And also how accurate is the resulting approximation. So we did a little bit of that in 361, which is basically the numerical differentiation part. So the idea, as we recall, is that we're going to be working on interval from 0 to 1 by a simple linear transformation. This can be an interval from any a to any b. We are going to, let me put 0, 1 up, 0, 1. The goal is how to approximate ux, all right, ux, which we did already. Let's subdivide this interval into, I'm going to use slightly different notation, x0, x1, all the way to the end is xm plus 1. So here is xm, right? x2, so on and so forth. We assume it's uniform. So we're going to use m plus 2 nodes, right? And the distance h is 1 over m plus 1, over m plus 1, plus 1. The xi is equal to I times h, right, as we did. So the reason to use this weird m plus 2 nodes instead of m nodes, of course m can be any number, so it's just notation, is that in the end we know u at x0, right, and we know ux at xm plus 1 for the Dirichlet boundary condition case. So we only need to solve. So for some cases, this guy is known, this guy is known, and what we only need to solve is this guy in the middle. So that would be exactly m. So we're going to get m unknowns. This is to be consistent with the textbook. So we ended up having a system for most of the time of size m by m. So from numerical differentiation, we know that u sub x is derivative of x at xi. Okay, this can be approximated by the divided difference, which is uxi plus h minus uxi divided by h. Okay, this as we recall, we use d plus u to denote it. We also have d minus u, all right, which is uxi minus uxi minus h divided by h, and we have d0 u, which is uxi plus h minus uxi minus h divided by 2h. As we did last semester, now where I'm now reviewing is that for the accuracy, we're going to use the tool, our favorite tool, which is Taylor expansion. Okay, Taylor expansion. That's basically the only tool we need for the class. So we have that for example, the d plus u at xi, right? This is equal to u of xi plus h minus u of xi divided by h. We're going to expand. Remember, Taylor expansion is to expand a function around a location, right? Around location. So we call f of x around alpha, right, is equal to f of alpha, okay, plus x minus alpha f prime alpha plus x minus alpha squared over 2 f double prime alpha plus in the generic term is x minus alpha to the n divided by n factorial f to the nth derivative at alpha, and this goes on and on. So in our case, the alpha is xi, x is xi plus h, so that means x minus alpha is h. All right. So make sure to review the Taylor expansion, Taylor series, and also, as we did many times last semester, if you were to stop somewhere, and what is a error, right? What is error? So this is equal to uxi, the uf alpha plus x minus alpha is at h times u prime xi, but I'm going to stop here and simply use a big O notation, order h squared. So anything I'm not writing down is they all have x minus alpha squared at least, and h is small, so h squared is even smaller. So maybe let me write here. When we use big O notation, what that means is that something of a function of h, another notation, it's just notation. This is, if it is written as big O of p of h, what that means is that my limit, if I divide gh by p of h, and my h go to 0, this guy is a constant. So intuitively, it basically says gh and ph asymptotically they have the same size. Okay, same size. It's just a multiple of that. So what we neglected is a multiple of h squared. Okay. This minus uxi divided by h, right? Divided by h. So of course we're going to cancel this and that, which brought us to so d plus u xi. This is equal to h cancels h, u prime at xi plus order h. It was order h squared divided by h. It got order h. Order h. So this means that, well, the d plus u at xi is not going to be exactly equal to the derivative at xi, but it's an order h accurate approximation. So this is order h accurate approximation to u prime at xi, right? That means if h is small, the difference is small. So that's key for our numerical class. We were not looking for exact solutions. We're not looking for exact quantities on the way. We just settle with something approximate, but with reasonable accuracy. That is tolerable, right? You can simply play with this, which you will be doing in the homework. So if you are given a function f of x, which is say cosine x, right? Cosine x, and you are going to split the intervals into 10, 20, 40, 80, and so on and so forth intervals. Right, intervals. And so this is on 0 to 1. So your h is going to be 1 over 10, 1 over 20, 1 over 40, so on and so forth. Right? So you can certainly calculate your d plus f at 0.5, for example. All right, this will be we'll use 10 elements, 10 intervals, where we'll talk about f, evaluate cosine at 0.6 minus cosine at 0.5 divided by 0.1, right? And if you use 20, we're going to get cosine, so the f above is just cosine for this particular example. So it's when it's 20, it's 0.05, so it's cosine 0.55 minus cosine 0.5 divided by 0.05, and so on and so forth. Right? This is and then you can take the difference, right? The exact value, we know the exact value. Cosine, the difference is a negative sign, so it's a negative sign of 0.5. So you take the difference, you get the error, right? And you will see the error. Your error is getting smaller. It's getting smaller. And the homework will be to play with that, see how do you visualize the trend. So the error is getting smaller. Is it getting smaller? If yes, how quick? How quick? In other words, as you double, one measurement is as you double the number of intervals, is error halved or what? Okay, those are things to work on. I need a challenge. A homework problem. So, by the same, pretty much exactly the same procedure, we're going to get the d minus u is going to be order h, and d0 u is going to be of accuracy order h squared. Okay. And what's going on here is a pretty interesting phenomenon. Is that when we're taking xi plus h, then we have xi here. We're taking xi, that means plus h here. It was minus h, so it's so-called centered, right? This is a reference in the middle, so it's centered. When we have centered type of scheme, usually that means cancellations, and which leads to higher order of accuracy. High order of accuracy. All right. So you may wonder why this one has high order h squared. That's much better, because if h is 0.1, this is like 0.01, not like the error for the d plus diagonal is still 0.1. Okay, much smaller error. And why? If you do tail expansion, you'll see. Okay, you'll see. So basically, what we're having is that we have u xi plus h minus u xi minus h divided by 2h. What is u xi plus h? That is u xi plus h u prime xi plus h squared over 2 u double prime xi plus, notice that this time I wrote one more term. I'm doing the big O h cubed, right? And this minus the next term, which is uxi. Here, if you go back to the Taylor, what I just wrote out, the Taylor's expansion, the x is xi minus h, alpha is xi. So the x minus alpha is negative h. So the minus h u prime xi plus negative h squared becomes positive h squared over 2 u double prime xi plus, in the future, I'm going to neglect the evaluation xi part. When we write down u double prime, it means add that xi. This divided by 2h, okay? So there's some cancellation going on. Xi cancel with xi. And h squared, remember before it was all inside of that order h squared. Now if you expand it, for this particular case, it can actually cancel. Okay? And this will be equal to, so h minus h, the 2h, so it's 2h, and cancel with 2h below, that becomes u double prime, u prime at xi, right? If you're wondering whether that or h cubed term is cancelling, the answer is that they are not. You can see there's a pattern. The odd terms are not cancelling. The even odd terms are cancelling. The odd terms are not cancelling. Okay, what we're having is that we're going to get h cubed over 6 u triple prime, right? Minus inside h cubed over 6 u triple prime, that's 3 factorial, divided by 2h, right? Now if you do one more term, this means what we have left is order h to the 4th, and h to the next guy will cancel. So we're going to get 5th over 2h. Alright, so what this is that this is u prime at xi plus h cubed over 3 and divided by 2, that's h cubed over 6, and cancel with h, you get h squared over 6. Okay, u double prime plus order h to the 4th. So that's this term is a leading term of the arrow, which means this is order h squared. Okay. Let's finish today's lecture by starting a few standard techniques that would lead us to a more general schemes. So we don't have to just use a point on the right or the point on the left or both of them. We could use more points basically. So which is we can do a wider stencil. This we call stencil. So the stencil for D plus, the stencil for D plus, it was xi plus h, xi plus 1, and D minus is xi minus 1, xi, right? And D0 is xi minus 1, xi plus 1. Okay? And the question here is, why do we have to restrict ourselves on just those? For example, maybe we can use more points, right, to get higher accuracy. For example, we can do a D2 uxi. We're going to use the stencil will be xi plus 1, xi plus 2. How about that? of course, the symmetrical one would be xi minus 1, xi minus 2. That doesn't matter. So we will get, as we saw above, it's going to be a linear combination of those, of the function values at the stencil points. So we don't know them, so let's assume it's a u xi plus b u xi plus 1 plus c u xi plus 2. Right? The goal is this is approximately equal to the goal. Remember the goal is the d2u at xi. This should be approximately equal to u prime at xi. Okay, at xi. How do we do that? Right? How do we do that? So we would have to find out a, b, and c. Right? A, b, and c. And the goal again, surprise, is that still Taylor expansion. So we have u xi, right? We're going to get u. Remember in the goal, there's a reference is at xi. Well, the goal is to find something to walk around xi. So the expansion, the Taylor series expansion, that alpha is always xi. So the uxi plus 1, this guy is equal to uxi, right? Plus h u prime plus h squared over 2 u double prime plus h cubed over 6 u triple prime plus order h to the 4th. And uxi plus 2, this is uxi, right? So the distance between xi and xi plus 2 is 2h. So that x minus alpha is Taylor expansion is 2h, not h. Plus 2h u prime plus 2h squared, which is 4h squared. 4h squared divided by 2 u double prime plus 8 h cubed over 6 u triple prime plus that. And what we do next is that, well, we are multiplying this by A, we're multiplying the second by B, we're multiplying the last by C, and add them up, and add all of them up, okay? Add all of them up. So, of course, you can see we're going to get A plus B plus C, uxi, all right? And for u prime, we're going to get BH plus 2CH u prime, okay? Plus u double prime, we're going to get BH squared over 2 plus 2, 4 over 2 is 2, 2CH squared u double prime. Right? Plus we don't really need the cubic term or the h cubed. And we want, remember the goal, right? The goal is this should be approximately equal to u prime. So by matching the coefficients, we know that this guy must be 0, and this guy must be 1, otherwise it's not equal to u prime. And this guy, we can make that guy 0. Okay? Then that linear combination is order h cubed. Of course, so far, right? Of course, we have ABC. If ABC has 1 over h in it, then it's not really order h cubed. Because this here, there's A, B, C in it. So this means that we got a system of 3 equations. A plus B plus C is equal to 0, right? And we get B plus 2C is equal to 1 over H. We get B over 2 plus 2C is equal to 0, right? Equal to 0. So this we can easily solve that. This means that so the B here is negative 4C, right? Negative 4C. You put that into second equation, which becomes negative 2C is 1 over H. So C is negative 1 over 2H. B is negative 4 times that. So that's 2 over H. Alright, 2 over H. And A plus B plus C must be 0. So B plus C is 3 over 2H, right? So A is negative 3 over 2H. Which means, what we just did is that we know U prime and Xi can actually be approximated well by, we have 2H, we're going to have negative 3 U Xi, right? Plus 4 U Xi plus 1 minus U Xi plus 2. Alright, Xi plus 2. And that's order H squared approximation, okay? Because again, that order H cubed has ABC in it, so it's for example, B times H cubed over 6, and B has 1 over H in it, so that H cubed becomes H squared, okay? This method that's the method of undetermined coefficients. All right. We're going to next class. We'll derive a generic formula for that method. So which is you give me any stencil to approximate the derivative at any location. You always find a way to solve for the coefficients.